In our previous video, we looked at the brute force Monte Carlo method. In this particular video, we're going to look at Q learning. So Q learning is an off-policy learning where the estimated future Q is the maximum possible reward at any given state. So it looks at the ideal. And so when we look at Q learning, what we have to do is come up with a Q function that's the expected value of the current award that comes with a current action and future possible awards that come with actions that would come after the decision we're currently making. And when we set our Q learning process, we define some hyperparameters like the learning rate, which is how much emphasis, how much weight is put on those future rewards versus the current reward in the calculation. So in this particular video, we are going to do Q learning, and we are using our frozen lake example where we have a starting state and we are up in the top corner of the grid. We want to get to our goal at the bottom, and the challenge is we're walking across the ice and we have a number of places in the lake where there are holes in the ice. And so the key is to find the path to get to the goal without falling in the lake. So how do we do this? Well, we are working from our reinforced learning workbook here. You can find that at drstephpowers.github.io/BIA. Right here where it says reinforced learning, because reinforced learning is used for prescriptive analytics. What should the organization do? Well, in this case, what route should we take to get to the goal, to get across the lake? All right, so we are in the section here called Q learning, but just a reminder, if you didn't watch the previous videos, we need to install Gymnasium to run this frozen lake example and import Gymnasium as gym. We are also importing T-range so we can track our progress. And then the other thing we need to do was we need to create the environment. So we use gym to make a frozen lake. And the default here is that the frozen lake is 4x4. You can see an S for the starting, G for the goal, and F for the frozen parts, and H for the holes. And so we're looking for the routes through this that will get us to the goal. And when it comes to this, there are 4 actions. You can go up or down, left or right. And because it's a 4x4 grid, we have 16 states. So we need to initiate this set of code here before we can do our Q learning. In our previous video, we looked at the brute force method to find the solution. And we did 100 simulations, and for the most part, everybody fell in the lake. So we were not getting a very good score at solving this particular problem. We found they kept falling into the hole. And in fact, in the last couple, when we've done it, nobody has finished it. They all ended up in a hole. So our score here is 0. All right. With Q learning, the first thing we got to do is create a table for Q. We're going to start with it being an empty grid, and it is going to be 4x16 because in this case we have 4 different actions, right? Up, down, left, right, and we have 16 different states that are the 16 different points on the 4x4 grid. The next thing that we do is that we need to define our hyperparameters. And so you can always play with changing these to see what happens. So we're actually going to iterate through this. We're going to do 20,000 simulations instead of 100. Okay, 100, we got, it was easy to see the percentage that made it, but the score was pretty low. So let's do some additional iterations to see if we can get some who make it to the end. And then we talked about how when we do Q learning, we have a learning rate. And when it comes to that learning rate, that's the alpha we were talking about just a couple minutes ago. This is the weight put on how much of the expected value is past information versus the new information. A larger alpha puts more weight on the future. So here we have a higher alpha, an alpha of 0.7. And so it's putting more emphasis on what that ideal outcome is and the actions, the rewards that come after. We're going to allow a certain number of steps. So how many times, because if you're looking at this frozen lake, let's just go back to a visual of the frozen lake. How many steps are you going to allow them to do it? So if they have to solve it, say in 10 steps, 1, 2, 3, 4, 5, that's great. Are we going to allow more than that? So we're going to start with a scenario where we can allow up to 99 steps, which means you can go back and forth and back and forth and back and forth before you finally make it. So in this case, you got to decide what is that maximum number of steps that you're going to allow in each single simulation. We have a discounting rate. We have an exploration rate. And so when we look at the actual Q learning calculation, the Q learning calculation looks at this is the existing state plus this is the future state. And so we can see that learning rate, that alpha, and how much we're taking into consideration that future state, right? So we're putting that at a 0.7. And then here we have this NP max with the Q learning. Remember, it's looking at the ideal. So it's looking at the maximum possible reward we could get from those future routes that we could take. And gamma then is going to adjust that maximum at ideal state. And so if we go back here, this discounting rate is how much we're going to reduce down that ideal. And so here you can see the discounting rate gamma 0.95. We're basically going mostly with the ideal state, okay? We have epsilon. So here we have related to exploration. So when we look at the role of epsilon, the role of epsilon is in the random movement. Okay, so what we're going to do is we're going to randomly generate a number between 0 and 1. If that random number is bigger than our epsilon, because remember it's a percentage we're generating, if we get a number that's more than epsilon, then we'll go with the ideal state. Otherwise, we are going to move randomly. Okay, so this is going to determine the amount of exploration as we change this epsilon. So you could change this number down, and that would then be that we would take more of that ideal route as opposed to more random movement. Okay, now let's go back. Got stuck there here. Then we have probabilities. We talked about when we just talked about our Markov decision here and the process that we follow is we talked about how each action has an associated probability of being selected. And so that's where this is coming from here. This is the probability. And so as we were exploring, these are the probabilities of these different routes, okay? And then exponential decay for exploration, because the idea is that the more you explore, the more you know. And so the probabilities should be changing the more steps we have taken. All right, so let's run our Q learning algorithm. So we're going to start with this empty table called rewards. We're going to use that T range so that we can have a progress bar on the bottom. We are then going to loop through, and we are going to loop through it 20,000 times, okay? So we're going to run this simulation 20,000 times. Each time the environment's going to reset, starting with a state where we are at that top corner, okay? And then what we're going to do is we're going to start at step 0, and we're going to count and move forward. So this is going to allow us, as I was talking about in the previous video, we can actually track how many steps the different scenarios take. We start with done equals false, and that's because what we're going to do is we're going to move through this until done is equal to true, because at that point you've either fallen into the lake or you have reached the goal. Okay, and this is going to allow us to track those number of steps that we get there. Okay, so what are we doing here? We're looping through steps up to the maximum step, so up to those 99 steps. We're going to start at 0 and go through, and we're going to start by randomly generating a number. If that number is greater than epsilon, then we go with the ideal action. Otherwise, we're going to randomly select an action of up, down, left, right. Okay. When we do that, that puts us into a new state. That new state has a reward. It's quite possible that new state is a hole in the lake, in which case done will be equal to true. And so then what we're going to do is we are going to use our Q learning equation, where we take our current state and then we learn from the future potential rewards we could get of the outcomes from the states that would come after. And so you can see here, right, we talked about how the Q learning method goes with the ideal. That's why we're using this max here. Okay, it's the maximum reward given all the possible outcomes. We're then going to update the rewards based on our new state. We will update the state we are in to our new state, and we will assess, are we done? If we are done, we fell in the lake, then we are going to print out we fell into a hole. If we reached our goal, we're going to print out we reached our goal and the number of steps that we made it through the process once we have reached one of these two outcomes. Okay, our epsilon is going to update. So remember, epsilon here is this exploration rate. We start at 1, but remember how here, if the random number is greater than epsilon, then that changes our behavior. Well, this epsilon is going to adjust over time, because the more and more we explore the table, here's that exponential decay that we talked about a moment ago, the more we know about it, the less we need to explore. So that is going to change. We start here, this exploration rate, and then that exploration rate is going to adjust. And it's going to decay the more we've explored, the less we need to do more exploration. All right, and then we can track the total rewards. So what we're going to do is we're going to print out our score over time as the sum of the rewards divided by those 20,000 simulations we go through. So we're going to track it and see how well we do, and we'll be able to watch as the different simulations, whether they reach the goal or fall in the hole. So let's run that, and then let's show what it's doing. So you can see here as we run through the different scenarios, you can see the ones that have fallen in a hole. So you can see the red is signaling which hole they fell into and how many steps before they fell into the hole. So for example, we can see this one fell into the hole at step 14, step 24, step 30. They all seem to keep falling in the same hole. Seem to kind of be stuck. They do reset, right, each loop back to the same starting position. So they should be moving across the board. Have we seen any yet that haven't fallen into the hole? All right, let's see how it did. I ran this before and I got 50% score. Go to the very bottom of this. No, nobody made it. All right, let's try this again. All right, maybe we got a gym that isn't particularly successful here. Let's randomly generate our gym, our number of states. Let us create our table here and enter in our hyperparameters. And then let's iterate through. Oh, there you go. So now there's a couple. Sometimes I think I randomly generate a pond layout that just nobody can win. But here, you know, you can see them come through. We can see that there's a couple that are winning now. With 13 steps, another one that died after 71 steps. Here one went 1 after 47 steps. There we go. So we'll let that run, and then we can see, if we scroll towards the bottom of this, we can see that progress bar that we added. So you can see 64% complete. It's updating periodically, 70% complete as we go through. You can see more of them that are making it to the end. So we'll just give it a minute as it goes through. 81% complete, 90% complete. So remember, I know we did our brute force, right? Nobody won. This one here, the best score. So we got 50% of them actually completed the path. And so the piece that you see here is actually the Q, learning the Q table here, where we have the 4 different directions and we have our 16 states. So we can see as we work through this to find a solution, to find a proper path. You can run the simulations many times until it kind of figures out the better path. And here it was able to finish the challenge 49% of the time. So we could dive deeper into this, figure out who was able to solve the problem in the least amount of steps, looking for the best route for the process. In the next video, we'll look at SARSA so that we can compare.